In this lesson, we're going to look at the mathematics behind an incline. And in order to do that, we have to examine exactly the angle that an incline is at and how that affects our calculations of acceleration and forces. On an incline at angle theta, say some angle theta, we have an object that is sliding down a frictionless incline. So this will be no friction, mass m. So it's going to slide down in that direction. The problem comes with this. If we look at our coordinate system, which way is the object accelerating? It's accelerating in the negative y direction and in the positive x direction. The problem there is that now I've got to calculate components of the acceleration in the x direction and in the y direction. So what do? Well, here's what we can do. We can tilt our coordinate system to match our incline. It's perfectly valid to do this. The coordinate system doesn't know any better. As long as you're consistent with x being everything parallel to the incline and y being everything perpendicular to the incline, the mathematics will work out just the same. And in fact, not only does this have an advantage of having the acceleration act in only one dimension, as you can see now, the acceleration will be only in the x direction. But the normal force will now be in the y direction. Normal force, normal meaning perpendicular, the normal force is always normal to a surface or perpendicular to a surface. Floors can only supply forces that are perpendicular to them, walls perpendicular to them. So an incline can only supply a force in this direction. So the normal force is now in the y direction. So we've got a win-win there. However, there is one drawback, and that drawback is gravity. Gravity is still going to point straight down. And when gravity points straight down, it's not in the x direction and it's not in the y direction. It is perpendicular to the ground, but that's the one thing we're going to have to break into x and y. And that's going to be represented by mg, as I wrote there, mass times gravity. That's the weight of the object. So the weight of the object acts straight down. It's a small price to pay for a simplified form of acceleration, and it will be much easier to calculate. What we're going to do now is look at how we get the components of the weight parallel and perpendicular to the ramp and to the direction of the mass. So what we're going to look at now is I'm going to redraw that down here. There's the ramp. There's the incline at angle theta. And there's the object. It has a weight headed down this way given by mass times gravity. We have our coordinate system that's tilted. So I've got my y and x direction here. There's y, there's x. And in fact, the mg points down, straight down like this. What I want is I want the component parallel to the x-axis, okay? That's going to be mg in the x direction. And I want the component perpendicular to the ramp, which is going to be the component in the y direction. Right there, and you notice they're perpendicular to each other, as they should be, as because x and y are. Well, that's great. Now I've got a right triangle. MG is the hypotenuse of the triangle. MGY is one side, and MGX is the other side. Question is, what is this angle right here? And that angle right there turns out to be this angle here, right there. And you can show that using some simple geometry. And I won't go through it right now, but you can show that using some simple geometry. And the MGY and the MGX that I drew, I'll draw them over here. This is MGY, mgx here, mgx, and this is mgy here, mgy. And the angle in question is the same angle as the ramp, which will be theta. Well, that makes it convenient because now we need to find out what these components really are. As you can see, mgy is the adjacent side of this triangle. If we look at this triangle on its mounted on its base, we have mg as the hypotenuse, mgx here, there's theta, this is mgy. We can see that the cosine of theta equals the adjacent mgy over the hypotenuse, or mgy equals mg times the cosine of the angle. That's maybe different than what you were used to looking at. Ordinarily, we associate cosine with x, but that's because the angle is referenced to the y-axis. Consequently, we can also see that the sine of the angle is going to equal the opposite mgx over the hypotenuse, mg. Or we can say, let's put a little division there, or we can say that mgx is going to equal mg times the sine of the angle. So these are two of the forces on that incline that affect the object. This causes the object to slide down the ramp. As you can see the direction of the arrow, mgx points down the ramp. This slides it down the ramp. This object, this equation shows is the amount of force that the object presses against the incline with. Let's look at another picture of the object by itself. In other words, a free body diagram. Here's the object. What we're saying is there is a weight pulling it down the incline in this direction that's going to equal mg times the sine of theta. Part of its weight is going to be pressing it against the ramp. That's going to be mg cosine of theta, the weight times the cosine of the angle. And then the normal force provided by the actual ramp is going to be pressing back against there, and that's the normal force. You can see from this simple case that if there aren't any other forces present, you can see that the normal force in this simple case is going to equal mg times the cosine of theta, and not the simple weight, not going to just be the weight, it's going to be mg times the cosine of the angle. But this is going to be the force accelerating it down the incline. And in the next example, I'll show you how that works.